So now that we have shown the application part of the tool flow, we'll quickly go to the hardware part. So that's this part of the tool flow where we go from a high-level abstract description of the hardware, we can actually synthesize into a FPGA bit stream. So, as shown before, the hardware platform we choose was a 5 processing tile platform with a DDR connected, some DVI, Ethernet, and interface to the second FPGA where we have an accelerator running. So I won't show later on the use of the second FPGA, but I'll show you the quick generation of this platform. So if we take a little bit more look at the specifications, so we have 5 GPP tiles. Each of these tiles have around 256 kilobytes of local instruction data memory and quite a lot of communication memory, 320 kilobytes. So we have 64 megabytes of shared memory, so the DDR, and we have the DVI input and output running at 1280, 1024 at 60 Hertz. So this is actually very high resolution and gives you around 300 megabytes per second data stream. Furthermore, everything is connected with a 3x2 mesh that has 7 network interfaces. And this all has an impressive number of 82 ports. And to be easy to interface, to debug, to get screenshots out of the platform and data into the platform, we have an Ethernet connection, and that has its own microblade running an UDP server. So if we look at that, if we look at the tool flow, so we start off with a high-level description of the architecture. The tool flow will take this description and will try to expand it automatically to be complete. So this allows you to say, I want 3 DMAs and I want 6 communication memory that are each 1024 big, and then it will automatically expand this into separate elements. Once it has expanded this, it will figure out how the NOC should look and how the NIs and the ports and all should be hooked up together, and will generate the communication core. Once this is done, all the needed VHDL codes get generated, and we actually get a Xilinx project that we can synthesize. So I want to very quickly show this.
I will now give a quick demonstration of the hardware tool flow. Regrettably, we can't run the tool flow from beginning to end because the synthesis step will take several hours to complete. So the tool flow starts off with a high-level description of the architecture. So on the right, I opened up this description. So here we can see elements being specified, like the NOC should use a mesh topology of 3x2. We have a microblade tile MB1 that has 128 kilobytes of instruction memory, 256 kilobytes of data memory. We specify the other processing tiles. We add an inter-FPGA bridge, a shared memory. And using this high-level description, the tool flow will then expand this design, fill in all the missing information. It will then generate the communication core, so the network on chip, and in the final step, generate a full Xilinx project. So I will try to demonstrate this here on the left. So I type make Xilinx project, and this first does the NOC and then generates the whole project. So if we now look into the generated directory structure, we see a typical Xilinx project. So we see the XMP file, which is the settings for the project. We see the MHS file, which defines the top level hardware view. And we have the pcores directory that contains all the generated VHDL code. So we can open this project in XPS. So these steps will take quite a bit of time to complete. So normally on this laptop it will take about 5 minutes. So we'll cut the video and switch to the point it's loaded. Xilinx has now finished loading the project into XPS. So we can see here it loaded the complete architecture. We see here all the different elements of all the different processing tiles. But if we switch to the graphical view, we can nicely see our high-level description coming back. So here we have the different processor tiles, so MB2, MB3, MB4, etc. Here on the right we have our DDR memory. We have the DVI interface that automatically gets instantiated together with the memory. And here we have the inter-FPGA bridge. So from this point on we can click generate bitstream and Xilinx will synthesize this for the FlexTiles development platform. However, as said before, this will take a couple of hours, so regrettably we can't demonstrate it here.
So we have the CEA-LETI application we shown before. We now have our hardware, and this is one of the possible mappings we could get. So what we see here is the get image actor runs on one of the processing tiles, the pre-processing filter runs on one of the tiles, and then the CEA-LETI and CEA-LETI and the CEA-LETI direction each share a tile in both parallel versions, and then the rest runs on one tile. So you might think, why this mapping? Well, this mapping is based on analyzing the execution times. So I won't go into details there, but this is a same mapping for this application. And now we actually want to run it on a platform. So what you see here is the nice portable version of the FlexTiles FPGA board. And you can see here that we have the DVI in and the DVI out on the right side, and we have a lot of interconnect used for prototyping. So on the FlexTiles board, there are at the time when the project started, two of the biggest Vertex 6 FPGAs. Each FPGA has an Ethernet port. Each FPGA has two sets of DDR memory. We have a lot of interconnect, so we can add expansions board onto the FlexTiles platform. We have USB port. I see now that Ethernet has been mentioned twice. We have serial links, we have PCI Express links, and more. So for the final demonstration, this is how we currently have it hooked up. So we have the beamer connected up to the DVI out, the laptop an Ethernet connection, and we have our UART, which we use for debugging. As some of you might have noticed already, the presentations I gave on the second beamer already all went through the FPGA board, but I configured it with a platform that just passes the information through. So what I will now do is reprogram the board with this CEA-LETI application. Which will take a little while because each bit stream we're going to load into the FPGA is 19 megabytes big. And once this is loaded, you'll see the CEA-LETI application from the first part of the presentation running, working on this input image. So it's programming the FPGA, which will take about 40 seconds to get all the data into the FPGA. And then once it's running, you will see the same image again as processed by the Susan application, and it will quite quickly alternate between having the pre-processing filter and without pre-processing filter. So normally you wouldn't just alternate between the two, but this would be triggered by, for example, the overall light levels you measure. But now for demonstration purposes, I make it switch quite rapidly. So this is that's now slowly coming up, the version without. And as you can already see, it's very difficult to actually recognize anything in this image. If you look really good, you can see one or two cars, but that's it. So once the pre-processing image is enabled, so it expands the contrast, you see that well, the image becomes more clear and the algorithm can find a lot more features. So you might wonder why this isn't running in real time, because it takes about 10 seconds for each frame to render. Well, the big FPGA like this is nice, but an FPGA is still a prototyping tool. So each microblaze here only runs at 100 megahertz. But if you think like, okay, we're going to get a real processor here in silicon, this will be running a lot faster. Later on, also in the OFP demo, you will see the same application running, and you will see also there that it's running at real time. Okay, thank you for your attention. We will now move to the OVP part of this demonstration.